All right, so let's start from what we had done in the last lecture. Just to remind you that we had seen a very simple energy band structure where the density of states that you can see here is given by a uniform density of states, and my conduction band is bandwidth is about 1 eV, and the density of states is uniform. It's a very simplified density of states. And the energy gap is one electron volt here, and the conduction band is also symmetrical. The valence band is also symmetrical. It also has a bandwidth of 1 eV here, and the density of states is given 5 times 10 to the power 22 per centimeter cube per eV. So that's the dimensions of density of states here. And based on that, the fact that I have density of states, and I also know what is the probability of occupation of a particular state given by Fermi-Dirac function, we can multiply density of states by Fermi-Dirac function, integrate it from EC, from this edge to this edge, and we can get an expression for the electron density, and this is what we had obtained. The electron density for this particular case was given by N0, 1.3 into 10 power 21 exponent minus EC minus EF by KT. The reason we have put this approximate sign is that we had approximate the Fermi-Dirac function by simply an exponential, because we said that typically electron density here would be much smaller than the density of states, and this particular approximation then is reasonably valid. But still, it's an approximation, so that's why the approximate sign is here. All right, so this is what we had done in the last lecture, and this is the expression that we obtained, that the electron density, note, is related to the position of the Fermi energy here. Position of the Fermi energy with respect to the conduction band edge here. EC is the conduction band edge here. Okay, so let's continue from there. So in any semiconductor, then so now it's a simplified representation. Note that the previous diagram was E here and density of states here, and we were showing the density here and all that. So now I'm showing a energy band diagram where we have energy as a function, electron energy as a function of x here. X is within the semiconductor. We have EC. So we are denoting only the bottom of the conduction band. Of course, the band extends from this one here, and there are energy states above it. Similarly, EV is here. We are denoting the bottom, the top of the valence band here. And we said somewhere in the energy gap, EF is going to be there. The reason being is in the middle of the gap is because I have electron density. You can see from here, if I have electron density, which is much smaller than the 1.3 into 10 power 21, which is what is usually the case, then EC must be greater than EF, which means EF lies below EC. All right, and we can, for example, take 10 to the power 12 electron density, put it here, and then we will get a position of Fermi energy, which turns out to be minus 0.54 eV. So if you know Fermi energy with respect to EC, then you can get the electron density, or the reverse. If you know the electron density, you can find out where the Fermi energy is. Similarly, I can show you, say if N0 is 10 to the power 16, and now you would expect that the Fermi energy has moved closer to the conduction band. You can see this expression here. The closer the Fermi energy is to the conduction band, the higher the electron density here. Okay, and so we will find that the EF is now below EC by 0.3 eV here. So position of Fermi energy with respect to conduction band tells me how much electron density is there in my semiconductor here. That's the important thing. So that's what the equation is telling you, and qualitatively the position of EF with respect to EC. That's the information that is giving you how much electron density is there. Okay. All right. There is a particular, this is the expression that we obtained. N0 is 1.3 into 10 power 21 exponent minus EC minus EF by KT here. I can take this constant term now, and I can write it as N0 equal to some NC. It's a constant term, so let me just, you will see why I'm calling it NC in a minute here, what this NC means here, into exponent EC minus EF by KT, right? So all I've done is, instead of this number here, I've put a symbol here, okay? All right. Now note, Fermi-Dirac function, what does it tell us? It tells us the occupation, probability of occupation of energy, any energy state, right? So I can ask the question, what is the probability of occupation of an energy at EC? Right at EC. So that would be equal to 1 divided by 1 plus exponent EC minus EF by KT, right? And we know we have been talking about cases where we said EF is substantially below EC, significantly below EC, right? If we talk about those cases, then we know that this function can be approximated as exponent minus EC minus EF by KT. All right, so far is clear. So what then this equation that you see here, N0 equal to NC, exponent minus EC minus EF by KT, can be written as N0 electron density equal to NC multiplied by FEC. FEC is what? The probability of occupation of an energy state lying at the bottom of the conduction band EC. What is this equation implying then? If I look at it, N0 equal to NC FEC here. Now, in the form of a diagram, you can see this is what is implying here. It's implying as if, suppose, just for a moment, suppose that I had states only at conduction band edge, right? If I had states only at conduction band edge, so my conduction band was like a delta function, and the total number of states at that particular point would have been NC del E minus EC here. It's a delta function. If you integrate this with respect to energy, what will you get? NC. So what does this function represent? It says that I have total number of states in my system is NC, and they are like a delta function here. Now, if I had a system like this, how many electrons would have been there in my conduction band? How many electrons would have been there in the conduction band? Suppose my density of states had looked like this. It would have been what? N0 is equal to density of states NC delta E minus EC multiplied by the Fermi-Dirac function. And now when you integrated Fermi-Dirac function, at what point will you get EC? So won't you get this expression here? N0 would simply turn out to be NC into FEC here. So now what is the significance of NC then? What significance of NC are you getting? NC is like, note that this is my real density of states, right? So what people refer to NC is effective density of states. So what you're saying is your conduction band, you know, is more complicated, right? It has density of states like this. In fact, we can show even if it is not a constant, even if it's some other shape, the expression would finally be the same. N0 will still turn out to be NC exponent EC minus EF by KT. You can take any shape here. Yeah, you can take a, let's say, a linearly rising density of states. You can take a square root E, anything. All that would happen is the value of NC will change. That's all. The expression would remain the same. Okay. So what we are saying is the following, that N0 equal to NC exponent EC minus EF by KT. NC represents the effective density of states. It's as if you take all your states and you imagine that all these states exist at EC itself. All those states that are there, all these states are there. You imagine as if it exists at EC itself here. And then if all those states exist at EC, how many states? NC basically. And then you multiply it by probability of occupation of that particular state, energy state, and you get the total electron density. So the significance of NC is that NC people call as effective density of states. It's as if you have taken the entire band and you have collapsed it to a delta function here. All those states you have collapsed it to a delta function, and then the probability of occupation of that is simply NC into FEC. Okay, so that's the significance of what this NC is. It's called effective density of states here. Each semiconductor will have a unique value of NC. There will be a unique value of NC depending on what the nature of the density of states is and other details about the semiconductor here. Okay, so the important point then is that we have electron density in a semiconductor, which goes as NC, effective density of states, and exponential of the separation of Fermi energy from the conduction band here, where the Fermi energy is, okay, divided by KT here. So that's and each semiconductor will have a unique value of NC, which I will give you in a minute here, okay. Now, same thing, whatever I've said about electrons, same thing will happen with holes also. So let's quickly go over, so once more you'll understand where this equation is coming from if we repeat it for holes as well. Okay, so let's do that for hole density now. So hole density, now the focus is electrons are there in conduction band, holes are there in the valence band here. Now, Fermi-Dirac again tells us the probability of occupation of any energy state E, right? Now we are interested in holes, and holes represent what? The absence of an electron. So what will be the probability of occupation of any energy by a hole? 1 minus Fe, right? Fe gives you the probability of occupation of a state by an electron. So when I take 1 minus Fe, it would be the probability that the state is empty, state is vacant, and that vacant state is nothing but a hole. Okay, so FHE is what? The probability that an energy state E is occupied by a hole. So that will be equal to 1 minus Fe. And so all I do is 1 minus, we simplify, we write it like this here. And of course, I can write, rearrange the exponentials and write it as 1 by exponent EF minus E by KT. All right. So it tells us the probability that any state, and note our focus is on the valence band here. It tells us the probability of occupation of a state E by holes depends on this exponential here. So the further away E is from the Fermi energy, the lesser and lesser the probability is. Okay. So that's the probability of energy state E here. Now, how do I find number of holes in my valence band here? Well, again, I have a density of states. So number of holes will be equal to this GVE. GV is the density of states multiplied by DE. So that tells us the total number of states in a small energy increment. This is this here, multiplied by probability of occupation of that particular energy state here, FHE. So that's the total number of holes that would exist at this particular value of energy in this energy increment dE here. Now all I have to do is integrate it over the entire energy band, integrate it from EV down to EV minus 1. So I have to now integrate this from EV. We are starting from this band edge down to this band edge here, EV minus 1 here. So we have to integrate this here. Now the next thing that we do is we know that the Fermi energy node is going to lie somewhere in the middle of the gap here, and therefore this EF minus E will usually be very large, and the exponential can this term can again be approximated by simply an exponential. Under typical cases, you will see that EF lies somewhere away from the valence band edge here, and therefore EF minus E. Note that the minimum value of E is the maximum value of E is EV, and after that E keeps on decreasing here. So this function is very large, and therefore it can be approximated by an exponential here, and therefore one takes this here, multiplies by the exponential here, and then one simply does the algebra here, and it turns out to be P0 equal to 1.3 into 10 power 21, given the numbers here, exponent minus EF minus EV by KT. Okay, another way of writing this is P0 equal to some effective density of states in the valence band, exponent minus EF minus EV by KT. So the number of holes depends on how far my valence band edge is from the Fermi energy. The number of electrons depended on how far was EC from EF, and the number of holes is how far is EV from EF here. So exactly the similar expression here, P0 depends on effective density of states in the valence band. Okay, so two very, very important equations here. One giving you the relationship between electron density and the position of EF with respect to EC. The other one giving you hole density in terms of the separation of EF from EV here. Okay, so that's the picture that we have there. We have these two expressions now for electron density. Now note electron and hole density in equilibrium. Everything that we are talking about is in equilibrium. The concept of Fermi energy is valid only in equilibrium. Okay, so N0 equal to NC exponent EC minus EF by KT. P0 is NV exponent minus EF minus EV by KT. Now what these equations are telling us is the following. They're telling us that if you know N0, then you know EF, right? If you know N0, then you know EF. And if you know EF, then you know P0 as well. So both are, you can see here, N0 and P0 are related together. You can see it from this expression here. Wherever the EF is within the gap, that EF will determine the value of N0 and will determine the value of P0 also. So both are related together here, N0 and P0 here. Okay. And it's very easy to see that if I take N0 and multiply by P0, I will get NC, NV, exponent, EF drops out, cancels out, exponent minus EC minus EV by KT. Note that right hand side here, everything is a constant. NC is a material constant. NV is a material constant. EC minus EV is what? The energy gap minus EG by, and T of course is the temperature here. So what it's telling us is, all of you know this famous relationship that the product of electron density and hole density in equilibrium is a constant. Okay, so if you know one, you know the other one as well. Okay, All right. Now, so keeping in mind that EC minus EV by is EG, so we can write N0 P0 is NC NV exponent minus EG by KT here. All right. So we can write this out, and therefore we know if you give me a particular temperature and a particular material, I know the value of NC, I know the value of NV, I know the value of EG, I know the product here. Okay, and we give this product a particular name, and the name will come out as follows here. Let's take an intrinsic semiconductor. Intrinsic means I've not added any impurities to it, and therefore the only source, remember at T equal to 0, my valence band is entirely full and my conduction band is entirely empty. Now, if I have an intrinsic semiconductor, it's like a pure semiconductor, I've not done anything to it, and at a finite temperature, what happens is an electron from valence band goes into the conduction band. So what this tells us is that for every electron that you have a hole as well here. So for an intrinsic semiconductor, N0 must be equal to P0 and is equal to what we call as the intrinsic carrier concentration Ni. Okay, so N0 equal to P0 equal to Ni, and then if I take this and put it here in this particular term, it tells me what is Ni. That if I take a pure semiconductor, the electron density is equal to hole density, is equal to what I call as intrinsic carrier concentration, and its value is square root NC NV exponent minus Eg by 2 kT. So one can determine what the value of intrinsic carrier concentration is in a semiconductor if I know NC, NV, and Eg. And of course, Ni is a very strong function of temperature here. Not only that, T is a function of temperature, and you will see there is a dependence of NC also on temperature. If we go back into our expression, NC is also dependent on temperature, but it's a much weaker dependence here. This NC and NV dependence on temperature is weak, it's also under a square root, while this one is an exponential here. So what is basically telling is Ni increases exponentially with temperature T, and the proportionality constant is Eg by 2K here. All right. So you can imagine now, we've been seeing some of the quantities, and I said you can measure NC and NV and other terms also. You can see now that how I can measure the energy gap of a semiconductor. Right? Energy gap of a semiconductor. How? How can we measure? Suppose you make a pure semiconductor. How many electrons and holes are there? Ni. Right? And then what do? I measure the resistance of the semiconductor. Resistance will depend on what? How many electrons and holes are there? Right? And if I measure the resistance as a function of temperature, NC, NV, everything are relatively constant, and I plot R as a function of 1 over T, and then I will simply get the band gap there. So I will be able to measure how much is estimate the band gap by simply measuring the resistivity of a pure intrinsic semiconductor as a function of temperature, and you have the value of Eg here. Okay. Now, once you know Ni is this here, then this relationship that you see here, N0 P0, I can write it as Ni square here. Okay, because this is a constant, and the constant is equal to Ni square here. So if you have an intrinsic semiconductor, N0 of course is equal to P0 is fine, both are Ni. But if you don't have an intrinsic semiconductor, N0 can be larger or P0 can be larger than Ni, but the product always has to be equal to Ni square here. Again, I'm reminding you, this is at equilibrium. If I take a semiconductor and I shine light on it, then I have light will also generate electrons and hole pairs. I don't have N0 P0 equal to Ni square. My semiconductor is no longer in equilibrium. This relationship will not be valid. It's only at equilibrium. When there's no other external disturbance on my semiconductor, then this relationship holds here. Okay. All right. Now, as I said, all these relationships that you see here, N0 is NC and all that, I derived for a density of states which is given here. Right? I assumed a simplified density of states. And I mentioned that for a silicon, a more accurate density of states would be like this here, where it goes as, the conduction band density of states goes as GC goes as square root E minus EC. Valence band density of states goes as square root EV minus E. But I've also said that no matter what you take here, you take square root, you take whatever, the fundamental equations will again come out to be exactly the same. You can do the integral, except that mass becomes a little bit more involved. N0 will still come out to be NC exponent EC minus EF by KT, except that NC now, once I do the integral, note that NC will depend on all these terms that you see here. Okay, so NC will have equal to whatever 2 pi m by h square kt 3 by 2 here. So you can see NC is a function of temperature. But look at the dependence on temperature to t to the power 1.5. So it's a much weaker dependence on temperature here. So same equation, as I said, any density of states that I take here, I can take it as this is a square root E kind of a density of states. We showed you for a uniform density of states. I can take a delta function density of states. Any density of states will give you this expression, except that the value of NC will change. That's all. Okay, so this is a very general expression which is valid for all kinds of semiconductors here. Okay. Now note, the only thing which is important is that we have approximated the Fermi-Dirac function by an exponential. If I can't do that, then I will no longer get this term here. We assume that Fermi-Dirac function Fe was 1 divided by 1 plus exponential. And we said it can be approximated by simply an exponential. So that approximation is valid. If you can't do that, then this term expression will not come like this. Later on in this particular lecture, I'll show you what happens when Fermi energy gets very close to EC or even goes above EC. Okay, and what would happen then? Note that if Fermi energy gets very close to EC, what is happening? Number of electron density becomes very high, right? And I'm saying it goes even above EC, which means now we are talking about very, very high density of electrons. So in that case, these expressions then break down. They're no longer valid. But if you have, number of electrons which is considerably smaller than NC, then this expression is valid, and which is true most of the time. Okay. So same thing happens with holes here. P0 is equal to NV exponent EF minus EV by KT, and NV is given over here. A similar expression. This is for holes. Effective mass is for holes here, raised to the power 3 by 2. And Ni again is same expression. So everything remains the same. Whatever is the density of states here, Ni is same expression. N0, P0 is Ni squared. Everything remains the same. Look at the value of density of states. For silicon, it is 2.8 into 10 power 19 per centimeter cube at room temperature. This is NC, and NV is 1.04 into 10 power 19 here. So the order of density of states, to keep in mind, what is the order of density of states? You may forget the number 2.8 or 1.04, but the number that you must carry in your mind is that for silicon, my density of states, NC that you see here or NV that you see here, is 10 to the power 19 per centimeter cube. Okay, per centimeter cube. Which is also telling you is, when will these equations be valid? If my N0 is considerably smaller than NC, at least an order of magnitude smaller than NC, right? Then where will my Fermi energy be? Let's say N0 is less than 1/10 of an NC. So Fermi energy here would be, significantly below EC. And then your Fermi-Dirac function can be approximated by an exponential. All right. So keep that in mind, that NC is 10 to the power 19. Anytime I have electron density which is 10 to the power 18 or roughly or less than that, I'm okay. I can go ahead and use this expression here. Okay. That's why these terms are important. On the other hand, if you note the density of states for other semiconductor here, especially gallium arsenide is a very important semiconductor because it's a direct band gap semiconductor. Remember we had discussion that the conduction band minima and the valence band maxima lie at the same K value here. And it's important because you can get light emission from gallium arsenide here. Now, and also it's important because gallium arsenide has significantly higher mobility than silicon. Mobility values are larger, so it can be faster than silicon. Okay, but note something interesting. The conduction band density of states NC for gallium arsenide is 10 to the power 17. That's the order, right? Especially conduction band. Valence band is high, is also close to 10 power 19. But conduction band density of states is 10 to the power 17. What it means is the following, that if I have 10 to the power 17 number of electrons in silicon, right? In silicon, I can use this equation, right? Because density of states is 10 power 19. But if I have 10 to the power 17 number of electrons in gallium arsenide, N0 is 10 power 17 and NC is also 4.7 times 10 power 17, I can't use this. This equation will start giving me errors. In silicon, I can apply this equation when I have electron density equal to 10 to the power 18. right? I can use this equation, no problem, because Nc is 10 to the power 19 here. In gallium arsenide, if I have 10 to the power 18, what is this equation predicting then? This is 10 to the power 18. This is 4.7 into 10 power 17. Where is EF then? EF is above EC, right? And therefore my Fermi-Dirac function cannot be approximated as an exponential. I have to go and now use more accurate expressions to look at N0 here. So important point to remember is, what is my N0 with respect to Nc? What is my P0 with respect to Nv? As long as it is sufficiently below that, these expressions are valid. Okay, so sometimes errors can arise if you start using these expressions beyond their range of validity. It's always important that no matter which expression we derive, all these expressions will be based on some approximation. Analytical expressions are all obtained after some approximation here. And therefore, they will always have a range of validity. All analytical expressions, I'm making a very strong statement here, all analytical expressions, almost all that we will talk about, are based on approximations, and therefore they will have a range of validity. And therefore you should be aware of what is that range of validity. If I go very close to that boundary, now I should worry about it. And if you're far away from those boundaries, then these equations are fine. They'll predict, the predictions based on them will be accurate as well here. Okay, Ni for silicon is another important term to carry in mind here. So besides density of states, which is 10 to the power 19, the other thing to carry in mind is Ni for silicon is 1.5 into 10 to the power 10. So silicon, that's the intrinsic carrier concentration at room temperature. So this is another important term to remember. All right, there are some more. There are more concepts here based on intrinsic carrier concentration. So let's continue. There's a concept of intrinsic level EI. Okay, the idea is as follows. In an intrinsic semiconductor, we know that N0 equal to Nc exponent Ec minus Ef by Kt here. Now the position of the Fermi energy in an intrinsic semiconductor, I add the term I here because we're talking about intrinsic semiconductor. So wherever the Fermi level is, we are calling it EFI. So that's N0 equal to Nc exponent Ec minus EFI by Kt. The electron density is same as hole density. So we write P0 equal to Nv exponent EFI minus Ev by Kt. All right. Okay. From there, I can calculate where is this Fermi energy in an intrinsic semiconductor. All right. So we rearrange the terms. And it turns out EFI, the position of the Fermi energy in intrinsic semiconductor, is Ec plus Ev by 2 minus Kt ln Nc by Nv. Okay, that's where my Fermi energy is in an intrinsic semiconductor. First term is telling you is middle of the energy gap, right? Ec plus Ev divided by 2, which says middle of the energy gap. Second term tells you it's a little bit away from the middle of the gap by how much? Kt ln Nc by Nv. Now, Nc by Nv are so close to each other, this is 2.8 into 10 to the power 19, and this is 10 to the power 19. So we are talking about Kt ln times 2.8. So that's a very small term, and most of the time we just forget about it. We ignore it, and we say, note here, all the values that are given here, 2.8 and 1.04. Nc and Nv are all very close to each other here. So this term that you see here is small. If you want to be accurate, you can go ahead and calculate that, but most of the time we'll say the position of the Fermi energy in an intrinsic semiconductor is Ec plus Ev by 2. It's right in the middle of the gap. Okay, and that level, instead of saying EFI, that level which is in the middle of the gap, Ec plus Ev by 2, we also call it as the intrinsic level. So a level approximately in the middle of the gap, Ec plus Ev by 2, that energy level is being called as the intrinsic level. Why intrinsic level? Because that's where my Fermi energy will be if my semiconductor were intrinsic. Fermi energy would have been right in the middle here. So that's the significance of the intrinsic level here, EI. So when we draw energy diagram here, all right. So let's okay. So although we said no, sometimes what would happen is you will see that there is an N-type semiconductor. Right? And people drawing an intrinsic level, EI. And then you may be wondering, I have an N-type semiconductor and I'm drawing an intrinsic level. What does that mean? Okay. So although, intrinsic level is what? Is the energy which is in the middle of the gap. Ec plus Ev by 2. That's it. What we are saying is that energy happens to be the Fermi energy when my semiconductor is intrinsic. Even if my semiconductor is not intrinsic, I have an energy level which is in the middle of the gap all the time, right? So don't worry about it. If I draw an energy diagram and I show an EI, and then you say, this is an N-type, why are you drawing an EI? EI is simply now an energy level which is in the middle of the gap. And if the semiconductor were intrinsic, well, my Fermi energy would have been at EI. That's it, okay? So don't worry about if I draw EI at other times, okay? Now, once I have EI, this expression that you see here, now there are a couple of simple derivations from here. So N0 is NC exponent EC minus EF by KT. We can write as Ni. When I have taken intrinsic semiconductor, I have Ni equal to NC exponent EC. Fermi energy in an intrinsic semiconductor is at EI by KT. Right? So I can combine these two term equations that you see here and sometimes simply write N0 by Ni is equal to exponent EF minus EI by KT. Okay? It's the same expression that is here, but now we are writing it in terms of Ni here. So N0 by Ni exponent EF minus EI by KT. Okay? Alternative expression. Instead of this, you can use this one here. Here you need to know the value of NC to calculate N0. Here you need to know the value of Ni. Both are similar. One written in terms of EI, the other written in terms of EC. That's it. Okay. For an N-type semiconductor, N0 is greater than P0. What does that imply? Note that where is this relationship coming from? N0 P0 is Ni square. So now we are saying for an N-type semiconductor, N0 is larger than P0. What does it mean in terms of position of EF with respect to EI? N0 is larger than P0. So will the first term N0 by Ni greater than 1? Greater than 1. If it is greater than 1, where is my EF with respect to EI? Above. EF is above EI. Okay, so that's the point that I'm trying to make. When you see energy diagrams and anytime you see EF above EI, what do you mean? You know that particular region has more electrons than holes, right? So immediately the position of EF with respect to EI tells you that here. So if I draw now, look at the energy diagram. Energy with respect to X, I have EC, I have EV, EI. Where is EI? Right in the middle, EI. And I've drawn EF here. What does this separation tell us? EC minus EF. It tells us how many electrons are there. The smaller the separation between EC and EF, the larger the number of electrons. Another way of saying the same thing is what? What does this expression tell me? It tells me the separation between EF and EI also gives you the number of electrons. The larger the separation between EF and EI, the more the number of electrons. Okay, so that's an alternative way of saying it. It's the same thing. It's separation between EC and EF or separation between EF and EI. Okay. Now, whatever I've said for electrons, I can say it for holes as well. So P0 is NV exponent EF minus EV by KT. In an intrinsic semiconductor, instead of EF, I put EI minus EV by KT. And then I can write P0 by Ni equal to E exponent EI minus EF by KT. And for a P-type semiconductor, P0 is greater than N0, so EF is less than EI here. So that's what you would find. For a P-type, my Fermi energy would be below EI here. Below EI by a certain amount. And the further away EF is from EI, the more the number of holes in my semiconductor here. Okay. All right. Now, so we know now a little bit about electrons and holes inside a semiconductor, and we know how to. Yes.
You have written this expression for, like, you said that PI expression for PI will be same as like you are taking case of intrinsic semiconductor.
This is general. And then we said, let's take an intrinsic semiconductor. In an intrinsic semiconductor, number of electrons and holes are equal. So Pi is equal to Ni, equal to Nv. And then we put here intrinsic level, because that's where my Fermi energy is. So that's the equation.
Then how are you saying this last result?
I just take a ratio. I just take a ratio of these two.
You have these two expressions for intrinsic semiconductor.
No. This is for intrinsic. Only this is for intrinsic. This one is general. See, here I've made an assumption that EF is equal to EI, which means EF is in the middle. Then my semiconductor is intrinsic. At other times, EF is somewhere else. Okay, so this is a general expression. This is only for intrinsic, and I'm taking a ratio and expressing the general in terms of an intrinsic here. Okay. All right, so we know something about electrons and holes inside a semiconductor. We know that it depends on the position of Fermi energy with respect to EI, right? Let's go ahead and a little bit more now so that we move towards current density and we move towards understanding the current voltage characteristics here. Let's talk about potential inside a semiconductor. Can I write now, note what does EC really represent? EC represents the energy of an electron, right? And as I said, most of the time my electrons are at the bottom of the conduction band here. If you give them a little bit more energy, if you apply an electric field, the electron will gain energy, will have some kinetic energy here, and will try to go a little bit above, a little bit higher in the energy here. But again, it gets scattered and comes back and loses that energy here. So potential, as all of you know, is related to energy through this term here. Because we are talking about electrons, the potential will be minus 1 by Q. So I can write, see, EC is giving me the potential energy, right? Potential energy of the electron here, EC. And so potential, I can write in terms of minus EC by Q, some constant here, because it depends on what reference you are taking. For potential is always important. What is your reference? Okay. So this depends on some reference value, and it doesn't matter right now what this constant is. The point that I'm trying to emphasize is my potential inside a semiconductor is directly related to potential energy inside a semiconductor, which is EC. Why am I saying EC? Because I'm saying my electrons are predominantly close to the bottom of the conduction band. They don't go very far here. Okay, so that's why their energy is here. And normally when you don't apply any electric field, my electrons exist here and close to the bottom, and their energy, potential energy, is EC. Okay, and even when you apply an electric field, they go a little bit higher, but not by much. So the potential is related to minus EC by Q plus constant here. And the constant depends on the reference. And then you can also imagine that I can also write potential as minus EV by Q plus constant here. Why? If I write my electron potential in my inside the semiconductor is related to EC by Q, how can I get the second one? Well, how can I write? I can write this as EC minus EV, EC minus EV plus EV, right? EC minus EV is what? Energy gap, which is always constant. So all that I can write it as psi equal to minus EV by Q plus another constant. This constant, of course, is not the same as this, right? So I can also write it like this here. Psi is equal to minus EV by Q plus some constant here, some other constant, whatever it is. I don't bother about it. Okay. Note that absolute value of potential is never important inside the semiconductor. To calculate current, what do I need? Electric field is the derivative, right? So these constants that you see here, they will never bother you. What will always matter is what is psi 2 minus psi 1. It's always the difference in potential which will be important for you, not the absolute value. Okay. So minus EC by Q, you can write it as minus EV by Q plus constant, you can write it as. I can even write it as minus EI by Q. Where is EI? Right in the middle. So I can even write it as minus EI by Q plus constant here. So any of these definitions can be used for potential. You're free to use and say psi is minus EC by Q. You can free to say psi is minus EV by Q plus constant. You can free to say minus EI by Q plus constant. Any of them is fine for you. Another something interesting, field. Now, since I've used the symbol E for energy, for electric field, I'm going to use F here. Okay? Because otherwise there'll be confusion, and it's not easy to write another E. Formatting and all that is a little bit difficult, so more easy to simply write F here. And at many places in semiconductors, people use F. Many times they write a more curvaceous E here as an electric field. Okay, so I'm avoiding that. I'll simply write F for field. Okay, so field then is minus del psi by del x here. Right? Field is derivative of potential here. And if I take the derivative, note that the constant term will go away. So field equal to 1 by Q del EC by del x. So field at any point inside my semiconductor is what? The slope of my conduction band with respect to x. And same thing I can now, you can imagine, I can write F is equal to 1 by Q del EV by del x, 1 by Q del EI by del x. Okay? So these are very important things here. That psi is related to my EC or EV or EI through this term here, and my electric field is 1 by Q del EC by del XC. Okay, very important terms here. Okay. All right. If I take, now let's start looking at energy diagram here. I'm drawing EC as a function of X, EV as a function of X, EI as a function of X. Okay. How much electric field is there in my semiconductor? If I draw like this here. Note that, how am I answering? 1 by Q del EC by del X. There's no electric field inside my semiconductor here. EC is not changing, okay? So there's no electric field here. Suppose I draw like this now. All right. Is there an electric field? Where? Which direction? From left to right? Right? From left to right, note 1 by Q del EC by del X here. Does it make sense that this is from left to right? So we are saying that the electric field will be in this direction. Let's see whether it makes sense. If electric field is in this direction, in which direction should my electron tend to move? Okay, so suppose I have an electron, it should move in the, here in this direction. Does it make sense also? Because it's moving from higher energy to lower energy. So you can see these are consistent. You know, when I write F equal to 1 by Q del EC by del X, it predicts a field like this here. It says that electron should go in this direction, of course, from higher energy to lower energy. What about for holes? If electric field is in this direction, in which direction should the hole go? Should go to the right. Does it make sense? Because remember what we said, electrons, this diagram that we draw is in diagram in terms of electron energy. So holes like to go up in energy when you apply field. So hole will go like this here because of the field here. All right. So now when I draw an energy diagram like this, you immediately know there's a field. In which direction will electrons tend to go? In which direction will holes tend to go? Okay. Another important concept is, we have said here that in equilibrium, Fermi energy is constant. EF is constant everywhere inside my semiconductor here. Let me, one can show that through thermodynamic arguments that EF is equal to constant, but I'm going to show it in a different way. We have said that in equilibrium, the electron dense current is zero. There's no net electron current. Jn is equal to Q n0 mu n, F plus Dn del n0 by del x equal to 0. Electron current is equal to 0. All right. I know this n0 by ni is exponent EF minus EI by KT. In equilibrium, we know that this is true. So what I'm going to do is take this n0, put it over here, and take this n0, put it over here. Okay? I'm going to put it at both these places here. And I'm going to use this relationship. Psi is equal to minus EI by Q plus constant here. Why? Because field then will be equal to what? 1 over Q del EI by del X. Okay, so I'm going to do that. F is equal to 1 over here. And then I'm write this Jn here. So Q n0 I'm retaining as it is, mu n field 1 over Q del EI by del X plus diffusion constant. I've used Einstein's relationship, mu n into KT by Q. And then when I take derivative of n0 with respect to x here, n0 is here. I get del EF by del X minus del EI by del X here. Okay, I get this here. Simple, cancel out the terms here, and you can see that you can write as Jn equal to n0 mu n del EF by del X. Now this term by itself is important because note that in a semiconductor, what are the two driving forces for current? One is the field and the other one is the concentration gradient, right? This term encompasses both of them. What does it tell us? That what is a driving force for current inside a semiconductor? A gradient in Fermi energy. That's what drives. It includes within it, you can see here, when you write it like this, it includes within it both the terms here. The drift term as well as the diffusion term. It includes both of them here. That is the gradient in Fermi energy which will drive the direction of current. Okay. Fermi energy, in fact, if you go, is related to, for those of you, I'm sure all of you have done thermodynamics, right? Gibbs energy. Who remembers Gibbs free energy? Chemical potential. Anybody remembers chemical potential? So Fermi energy is nothing but the chemical potential. chemical potential, if you remember, gives free energy per unit mole, and it tells us what is the direction of a reaction, or in which direction things will go. This is what Fermi energy tells us, in which direction my electrons will go. Wherever del EF by del X is high, you can see it tells you the direction of electron flow here. The gradient in Fermi energy, or Fermi energy, is nothing but like the chemical potential. Okay. Now, since we are talking about equilibrium, what does this tell us? Jn equal to 0, and therefore EFX is constant. I have the same Fermi energy everywhere in my system. This is an extremely important result, that in equilibrium, what you do is you draw a constant Fermi energy throughout the system. Fermi energy cannot differ, because if there is Fermi energy differences, it implies flow of current, which violates our equilibrium condition here. Okay, extremely important point here. Fermi energy is constant throughout my system. All right. So here is an energy diagram that you see here, EC. Now I've drawn EF constant everywhere because it's an equilibrium. EI is here in the middle, EV is here. What type of semiconductor is it? Huh? N-type, because EF is above EI. Is there a electric field? No electric field in my system. It's N-type. Electron density, is it uniform? Is electron density uniform? Same everywhere? Because EF minus EI is same everywhere. So electron density is same everywhere, right? Okay. Now, I've drawn another, so now we know in a semiconductor, I have this conduction band edge, I have a valence band edge, I have an intrinsic level in the middle, I have a Fermi energy here, whose position tells me number of electrons and holes, and I've drawn one more level now. This is the level which we call as a vacuum level, E0. Is the value of energy outside a semiconductor, which is imagined to be a vacuum. Okay, so now you can see that this energy, what does this represent? Is the energy needed to take an electron out from the conduction band to the vacuum outside. So it's like I have a semiconductor, I'm ionizing it, right? I'm removing an electron from the conduction band and putting it into vacuum outside. Okay, this is a well-defined value which is called as electron affinity. In chemistry, you must have seen electron affinities and ionization potentials and things like that. This is similar. It's called electron affinity. So it tells us that I need an energy of 4.05 eV in silicon to take an electron from the conduction band edge and take it out and put it into the vacuum outside. Okay. Now, why this is important is because this is a constant. 4.05 eV is a constant. It doesn't matter whether my semiconductor is N-type or P-type. It doesn't matter whether I apply 1 volt to my semiconductor or 10 volts to my semiconductor. None of these things affect my electron affinity significantly. It's a constant. Okay, it depends on the nature of the semiconductor. All right, so electron affinity is an important term, and I've drawn one more energy level, which is the energy in the vacuum outside the semiconductor. Okay, now once I have this, there's another energy level that is important, is the separation of vacuum level from the Fermi energy, and that's called the work function. Okay, so the difference between E0 and my EF is called the work function of my semiconductor. So these are two additional terms here. So while electron affinity is a constant for a semiconductor, doesn't matter N-type, P-type, doping, whatever, none of these things will change. This one, work function, will depend on how many electrons and holes are there, because the position of the Fermi energy will change a lot. Okay, so the work function will vary depending on, so work function can be, I can have Fermi energy very close to EC, so work function can be about 4.05 EV. My Fermi energy can be very close to EV, so my work function will go to as 5 EV or so. So it can vary a lot, while electron affinity doesn't vary it. Okay. So once I have that, now note, potential I can write as E0 by Q also. Potential we were writing as EC by Q plus constant. Now EC is at a fixed distance from E0, always with electron affinity. So potential you can also write as minus E0 by Q plus constant here. Okay, another way of writing potential here. Okay, we'll stop here, but look at this diagram now. So you have an energy diagram I've drawn for some semiconductor, and tell me all the things that you can get from here. Electron density is varying. Okay, why is it varying? either by saying that EC minus EF is varying or EF minus EI is varying. Okay, electron density is varying. What else? Current is? Why? EF is constant. So, okay, so EF is constant, current is 0, my semiconductor is in equilibrium. You're saying I have non-uniform electron density. Okay, where is it higher? Where is electron density higher? Is it higher here and lower here? Right, is it higher? Okay, electron density is higher on the right side and lower on the left side. All right, what else can I get? Constant field. What is the direction of the field? Right to left. Okay, what else can I get? What else can you get from here? All right, so let's see. Equilibrium. Yes, everybody agrees. P-type. Is it P-type? Why? EF is always above EI. Everywhere. Note that EF is always above EI, which means everywhere in my system electron density is larger than intrinsic carrier concentration. Okay, P-type. Uniform N0, all of you have argued, no, it's not uniform N0. Can I get N0x? Actual value of how N0 is varying with X? Because note, this is linear and I've given you these two at, okay, you can get this. Potential, can I get? Because you know EC, so you know potential. Electric field, yes, you know electric field. Electron diffusion and drift current, can you get each one of them? Diffusion, how will you get? Once you get N0, you'll get diffusion. And drift also will be opposite of diffusion, so you can get that. Can you get P0x? N0 you said you can get. Can you get P0? How? N0 P0 will be equal to Ni squared, so you can get it from that. Or you can also get it, you know, EF with respect to EI, so you can get it from there. Whole current components, you should also be able to get. Drift current, diffusion current, all of these you can get. Vacuum level, do you know where it is? 4.05 eV from the EC here, right? So lots, if I draw an energy diagram like this, there are lots of things that you can get from here, right? Potential, electric field, N0, P0, a lot of interesting information. So you're seeing the importance of energy band diagram, and that's where we will concentrate in the next lecture, okay?